this morning. We said, the traffic may be a mess. You never know, right? The freeways. So we decided to do this first. Play it safe. So I don't know. It's sunny here now. It was raining this morning, right?
It poured here for like good 10, 15 minutes, a lot.
Same here. It's like, whoa. And now it's sunny outside, so you never know. It's almost like Colorado, unpredictable weather. Right? Yeah.
It was hot a couple of days ago. It was in the 90s. San Bernardino, inland, Pasadena, the valleys.
Oh, yeah. So when you go to work and it was warm, right, in Pasadena?
Yeah.
Yeah. Yeah.
Yeah, it's right next to the foothills. You're right there almost on the foothills.
Mm-hmm.
It's like La Cañada, Pasadena is northwest of Pasadena, so that's border. Yeah. They were telling us last week that there was a sighting, a cougar sighting, mountain lion at JPL.
Oh, on the park, in the area, on the JPL campus?
In the campus, yeah.
Wow.
And sometimes we get bears, but most of the bears or the mountain lions, they just wander off in the evenings. During the day, they don't.
They don't. But they just come down from the hills.
Yeah. But it's because
you back into the wild area, right? The rural area.
Yeah. Basically, we're right out on the foothill, just because where the building I work in is in the lower portion of the lab, and then the other buildings are up the hill. Literally up the hill, on the hill.
Oh, so they could get visitors.
Oh yeah, we get visitors all the time, and so they always post warnings. Oh, a mountain lion sighting last night, or a bear sighting. Say watch out.
Yeah, don't go eat lunch at the bench. Yeah.
and it's also like during lunch break, people tend during the warm days go to the hiking trails right next to it. And in the summer you have to watch out for the rattlesnakes.
Oh, I bet, yeah.
And then you during like these days, sometimes you have to watch out for the mountain lions or bears. So there's a lot of deer roaming around at JPL. So that's why the mountain lion comes down during the night and
for lunch. Yeah.
Wait, this is in
midnight snack.
Midnight snack.
This is in
midnight
Pasadena?
snack. Yeah, it happens here at JPL.
Oh wow.
All the time. There's wildlife.
You guys have cameras, right? So you probably catch a lot of those things going on. Yeah.
There's cameras all over the place. You would not believe it.
There's a little show, a bear or somebody coming down. Yeah.
Even security calls the people during the night that work in the night shift. Oh, watch out! Don't go out around this time because we just saw a cougar pass by, or a mountain lion, whatever, or a bear. Yeah, they call you. They're good. All the security, they've been trained, highly trained. Yeah, and there's a shooting gallery or whatever area where they can practice.
Like a range?
A range, yeah. There's a range there. So sometimes you hear like, whoa, what's that? Oh. During lunchtime, it's like, oh, what's going on? You hear all popping, but it's the shooting range. We're almost, I guess we're almost there, right? We can start.
Yeah, it's 11:10 right now, and I think maybe today, I don't know. So we only have 16 people on, but maybe somebody will come in late. So go ahead and introduce me.
I'm going to introduce you, Kenan.
Okay.
Then you can take over here. So, just a second. All right. So, good morning, everybody. This is Mr. Peralta. We have a special guest speaker today, and it's another alumni. So my goal was to get the most alumni as guest speakers because they have very good stories. These are handpicked people and leaders from previous years, and I'm happy to announce Mr. Kenan O'Neill, who was in graduated at 2013 from Oxford. Always a leader at all times. Helped the group in engineering, computer science. I don't know if you computer science and but mechanically as well. I think he was all mechanical, electrical, and so forth. But he was a true leader, like everybody else that I've invited. But he has a very interesting story about computer science. So happy to announce Mr. Kenan O'Neill, our guest speaker for today. And go ahead, you can take it away. And welcome.
Thank you, Mr. Peralta. So I'll go ahead and try to share my screen. Here, I'll do the entire screen. Oh boy. Of course, it's giving me a problem now. Allow. Okay, hold on.
Almost
I
there.
do not have permissions for sharing my screen.
Is it a permissions issue or?
I just
Yeah.
share their screen. So I got it over here. Let everyone share their screen.
That's
So that's
turned on, right?
It's on.
Huh.
You
Let
try
me
it
move
again.
Let me move it back and move it forward, okay? So maybe
Okay.
that's what. All right. So we'll see. All right. Hopefully that will work. Try it again. Did it work?
1 second. I need to. Entire screen. I'm getting a warning. Not allowed to permanently access your screen. That's fine. I'll just allow this one. Sharing. Yeah, I seem to be just having a problem with permissions. Let me double check my security settings.
There's only people invited to the host. Okay. Let me see.
Hello, Mr. Ikido.
Morning.
Good morning.
Sorry. I was on a company call.
Okay.
Crazy times.
Yes, that would be an understatement.
All right. I just reset it, but it seems to be the same. Let's see if I can find anything else here. Mr. Peralta, can you share your screen? Can you try and see if it works for somebody else
Sure. Let me see.
or anybody else actually from the outside? Because I'm just trying to figure because we never had this issue before.
Yeah, let me see
Let's see.
if I can share. So it's a matter of it's telling me I need to restart Firefox in order to do it, but I could share the link with.
Yeah, I'm able to share the screen.
Okay. So yeah. So Mr. Peralta, I just wondered because it's out of state and stuff. I don't know. Not that it should matter, but yeah. Okay. Is that you? No.
No,
Do
that
you
was
mind
me.
if I'm going
No, that
to go ahead. I'll have to jump off real quick and
Yeah.
restart Firefox. Okay.
Reset. Let's see. Okay.
Actually, can I practice
Ikido.
something I'm gonna present next week? Can I see if I can show my
Yeah.
screen?
So, as far as next week, let me see. Mr. Ben Morrill is going to present on the 13th. And
Okay, he's
yourself,
sharing.
Mr. Tom Hikito, Mr. Alonso.
Yes, I got it. I see it.
Okay.
Can you see?
Yeah,
Yeah.
yeah. And Mr. Peralta, I get it. So Mr. Hikito's presenting next Saturday?
Yes.
Okay. Thank you.
And Mr. Morrill on Friday.
Right. Okay.
Oh, sorry about
All right.
that.
No problem. You're on. Take it away.
Okay. So I'm going to be presenting on computer engineering and blockchain, kind of a more, trying to make it so that it's a little more distinct and talk about majors and just what I've more specifically focused on recently or in my previous job. So again, I'm Kenan O'Neill, and let's take it away. So some of my background, so I graduated from Oxford Academy in 2013. I then graduated from Syracuse University with a bachelor's in computer engineering in 2017. I joined Consensus Space right after I graduated. And then after joined Consensus AdTech and then Consensus Space once AdTech was, the project was completed or put aside. And then with the current economy, I was let go from Consensus Space and joined Aspen Mesh this last just a month and a half ago. So talking more about majors, so I was originally electrical engineering and I minored in computer engineering. I was forced to switch over when I talked to my professors and try to get more of an understanding of what I would need to do to minor in computer engineering, and they refused to answer and said switch over. It was one of the professors I was working with, and I really enjoyed his class, and he really wanted me in his major versus electrical engineering. So kind of my 2 cents is also when you're looking at majors, when you're looking at education, definitely go past the learning from the major. I did this and I did it through a gender inclusive honors, dry, no hazing fraternity. It was basically just an organization where we had people join and host events, learn more about other majors, mingle with people that you wouldn't normally be exposed to. And I became president of it, and I really enjoyed my experience with them, and it gave me a lot more exposure to outside people and the outside world. So I'd highly recommend looking into an organization, club, something to kind of go past that and get yourself a little bit more out there. So going more into this, what is computer engineering? So you have a little bit of a breakdown where you have science, which is the study of the world. You have engineering, which is more of the application of the world. So where a physicist can also do mechanical engineering or other types of related fields, they will be more specified into physics or more of the study, where engineers will be trying to apply it in every aspect of what they're doing. This is more of the focus of the curriculum and more of the focus of what you're trying to accomplish in like projects or whatever you go forward with. So kind of that's the basic of the foundation for computer science, computer engineering, all that stuff. So you have computer science, which is the focus of more the theory and the conceptualization of computers and computer programming. This usually tends to not touch hardware as much and more of software and trying to see how to make a computer work exactly how you want it to work and learning more after it has been produced. Electrical engineers, on the other hand, do basically all electrical stuff. So they touch the behaviors of electricity, they learn how circuits work, they learn how just a range of things from, you could learn power all the way to radio frequencies and There's even more with, say, semiconductor devices and things where it's production of computer components or production of electrical components. And then computer engineering is kind of the crossroads between them. It touches on the theory and the conceptualization of the programming languages and all that stuff, but it also goes into more of the hardware. So you interact with, you learn about electricity and how the behavior reacts with certain components and environments. So it's really the crossroads between electrical engineering and computer engineering, where you learn a lot of what computer scientists learn, but you also learn a decent amount from electrical engineering. So you know basically from electrical signal all the way until compilation what something's going to be doing. So continuing on that, kind of a little background into it. Electrical engineering and computer science is the crossroads, as I said. And you have electrical engineering, which was the original, basically computer science and computer engineering. Early days, it was basically you were an electrical engineer if you wanted to code, or you were an electrical engineer when you wanted to deal with computers, because that was the only outlet at that point. They didn't really have as much of the foundation. They didn't really build up as much until later. And then it progressed to computer programming, computer science. And as things became more complicated and you need to more specialize in that field, then computer science and all that popped out. So a little bit more of the distinction. You have analog circuits, which is usually what electrical engineers deal with. They also deal with digital. But the more trying to get more into detail is you have the computer engineers, which will go into detail. And this is the hardware aspect that comes with it, because this is a little bit more distinct, where computer engineers will pretty much focus on only digital. You could do analog as well, but it's just the bread and butter of computer engineering is digital. So you have logic gates and FPGAs. So what's a logic gate? So here's a little diagram. You have, this is basically just a logic gate or a transistor, which will build up logic gates, build up to logic gates. So you have just a basic behavior of, for an N type and a P type. So the N type, if you apply a voltage at the gate, it will allow current through from source to drain. And if you don't, it will block the current from going through to drain. So drain could be 0 at this point and 1 at this point. And then P-type is just the opposite. So it's just simple behavior. And this goes into, P and N-type go into a lot of chemistry and how you take a material, a semiconductor, and take silicon, make it into a semiconductor and all that, where it behaves to only transfer current in certain circumstances. So for P-type, it's the opposite, where you have source and drain, voltage applied, it breaks the connection, versus when there's no voltage, it allows it through. So this allows for communication and architecture of the computers, and just basically the very foundation. Transistors are the very foundation of everything else. And then you have FPGAs. So FPGAs are basically programmable gate arrays, which will allow you to change and modify how the hardware behaves. And you may be thinking, what about just a computer? And some of my experience with talking with people at Lockheed or other companies is, you could have a computer, but it's not as use case specific, and therefore is slower to usually perform certain operations. So where Lockheed had to process information, there was one application where it took a day for a normal computer to do, but with an FPGA, they did it in real time. That's huge. So it's just a matter of you knowing the application, and for specific use cases, you'll use a programmable programmable gate array, or you'll use a computer depending on what circumstances. FPGAs are not cheap though. So you'll only see it when they need to make sure it's efficient and able to do exactly what they need to do. And also, at any time, feel free to ask questions or whatnot. I cannot see any of the chat right now. So this is what digital basically looks like from a voltage point of view. So you have 0 and 1s, as probably many of you have heard, just computers work off 0s and 1s. And I could talk for a while about just this and breaking down the clock frequency, how you could tell it's going to hit 0 and 1 at certain points, and how it doesn't say 0, 0, 1, 1, all that stuff. So you usually have 0 to 5 volts as what a digital signal is, 0 to 3.3 for other applications. Just a basic overview of that. And as I said, you have logic gates. So this is the transistor split into a logic gate. And this is kind of, I don't expect anyone to really understand fully what's going on here, just because this is just building up off of that idea and saying, this is what it looks like from a diagram point of view, and this is what it looks like from a hardware point of view. So when you actually lay out transistors, this is what something it will look like. So you have 5 volts or 3.3 volts here, and that going into one transistor. In this case, those are p-type transistors. You have A and B, which provide the ability for this to transition into or allowing voltage through or blocking voltage. You have out and you have ground. So you could basically conceptualize it because these are in series, so 1, 2, and these are in parallel. So you have them separate. They're not relying on one another to send ground into out. And VDD is your 5 volts or 3.3 volts, and it will go through. So it'll either go down here or you'll have ground go through. But notice that you never see a combination of this where both ground and the VDD, the voltage, are going to go through to one another. It's always making sure, because that would create a short. So again, this is kind of breaking it down into more of a conceptualization, trying to show you how you could take something such as a transistor and have it where I apply either 0 or 1 to A or B, and it will result in a certain behavior, and how that translates to a physical diagram. Because so you have logic gates, and this was, if you look at it, you could tell A and B would have to be both 0 in order for voltage. Any other case, it would be it'd be ground, so it'd be 0 volts. So this is a NOR gate. So you have only when A and B are 0, do you receive an output voltage. So you basically put transistors in different configurations in order to achieve your desired behavior. And you basically have to figure out how to lay it out so that your p-type up here and your n-type behave in the desired ways.
So Kenan,
Yes.
so does the 4 represent the voltage that you're applying to the transistor?
No, this is just what I grabbed. I don't believe that should represent the voltage.
So why do you show a 4?
This was because it was the best diagram that I could find where it had a translation between a logic gate and the hardware physical layout. I don't remember off the top of my head what these would denote. It's been a few years.
Okay.
Yeah, so you'd have logic gates, which would then translate. So kind of giving you an idea of, if you ever seen Intel advertising or AMD advertising, you might see something like this, where you have all those logic gates starting to add up into something that can compute. So this is a very, very, very simple 8-bit processor. This is something that I did as a final project, and you'll notice there's a lot of repetition in certain things. And that's because you have, since it's 8 bits, you have to process. So this is so many logical commands at times. So you'll have 6 numbers or so, or 6, depending on the command. There's a whole breakdown here of, you'll have command versus useful information that's going to actually be used for processing.
So, how
yeah.
many transistors were embedded in that design to compute an 8-bit? I mean, thousands, several hundred.
Thousands, yes. I don't think it was several hundred thousand. It was one.
Probably.
Sorry, what was that?
Probably in the thousands or low thousands.
Yeah, low thousands. It was definitely, I didn't take the time to count. I did the bulk of all this wiring and all the layouts. And it was in the thousands, yes. But the good thing is, when you build these components, you could usually use them down the road. So if you build one gate, you could copy and paste it. You can use it in multiple applications to design it out so that you can have, you don't have to have a repetition of making every gate by hand. You make logical gates, you make different larger components, and then you could copy and paste them, as a few of these were.
Okay.
So by the time I got to that point, I had copy and pasted so many times that I lost track of how many.
Okay.
But if you actually look at this, and you can notice there's blue, there's pink, there's light blue, and there's a few other colors in there. And this goes into what metal or layer of metal you're using. So when you're laying this out, you don't want to cross over things, but sometimes you have to. So the idea is that you'll use different layers of metal. And the best way to go about it is by putting, say, layer 1 in one direction, layer 2 in a different direction, so that you don't have overlap. And you learn a lot of these tricks as you're building, or as you're learning how to make a processor, because it's very vital to know how not to cross metals that are of the same type, because then you could have a short, you could have information going into the wrong spot. It becomes very complicated into how you make sure that everything behaves, and you're working on a fairly small scale. Like you really have to zoom in to get the full picture of what's going on, and you have to lay out each one. So this is kind of going from all the way from transistor level all the way until like how you get into a processor. And this is where it's very distinct from electrical engineering. I know only a handful of electrical engineering students that took these type of courses. I know no computer science students, like strictly computer science from my school, that took these type of courses, because it's just, you don't go that low. And I could tell you propagation, I could tell you if you apply a voltage at one point, how that behaves, and you have to know different computer components so that you can get it to behave exactly how you want to. Anywhere from, you have a controller down here, you have, it goes on and on about like different things about how you interact with this and how you get it to be a computer versus just a bunch of transistors.
So mostly your material used was germanium, and then you can use gold and other metals, precious metals.
We weren't using any precious metals. It was just, when we laid it out, it was layers of metal. This was actually supposed to be these are made by the USC campus. So we'd send it out and they would make us a CPU and send it back. But when there is different behaviors of precious metals, and that's when it gets even more complicated, because gold has a low chance of rusting or doesn't rust. You have different precious metals which behave differently, and it becomes important because you have resistance of the metal, propagation delay, all that stuff that all play into a CPU when you're making it. So sadly, we didn't get to play around with different metal types, just the layers, but it gets to be a lot of information when you deal with metal types and N-type doped and P-type doped materials. So I hope that that answered your question.
No, yeah. I mean, I deal with some of these circuits as well, but not in the digital, more like sensors, and there are chemically etched using layers and passivations and doping and all that to create a certain voltage and certain current for each component or each or resistor, capacitor. You have to change the capacitance on some areas when you're designing circuits. So I even looked at these physically under a microscope. We have a microscope at work that goes up to 5000x. So I can really see all the intricate designs and line patterns on those circuits. So it's amazing.
Yeah, this was one of my favorite courses. This is specifically using VLSI, which is a very large system integration program. But as Mr. Peralta was saying, there's a lot more than just this to it. It's a whole other world.
Yeah.
So kind of taking a step back from this, you could kind of compartmentalize these components, and you could also simulate inputs, as you can see here, some outputs based off of where it is. Here's a controller, and you'll notice that this isn't attached to anything because it has signals either coming in from the outside world as you simulate, or you have it attached to these, but without having to physically put it there. And this gives you the ability to start designing things from like a component standpoint and package it up so that you can kind of make it into a black box where if this behaves properly, we're going to just wire it up to these other things, see how this behaves. And this is actually taken out of some of the simulation software where you do different behavior. So like you have move, you have load, you have subtract, all these different things that are described using ones and zeros, and you basically know by heart at some point what each command is based off of what the precursor information is, and then you have all the other information that's being fed in. And it gets into a lot of details and a lot of you have to be very meticulous and very, very particular about how you're doing this. And this is exactly what I was looking for in a major, so I'm very happy I went with it.
Okay.
So kind of going off of that, so you have the digital world, which we kind of talked about, and kind of go into computers and how transistors look and behave and all that. So then you have also the analog world. So this is more of the electrical engineers. This is more of what they deal with. You could also deal with it as a computer engineer, but it's not always, it's not stressed as much. So kind of giving you an idea, you can see it's very precise as zeros and ones. This is not, there's a bunch of things about this that are not precise when you want to break it down to more specifics. But then you have analog signals, so kind of giving you an idea, we did, as my senior capstone, we processed bodily muscle contractions. We put electrodes on ourselves and basically took these and determined when a muscle is contracting or not in order to operate a prosthetic arm. And this gets into a whole other realm of how to process that based off of your environment. So when you think about it, you have your wall outlet, which is putting out 120 volts roughly, and you have it at 60 hertz. Well, what we realize is when you're dealing with human muscles, the voltage for it is so low that you have to account for the 60 hertz that's being propagated into your body from all the electrical power around you. So we had to basically take that 60 hertz and we had to put a filter on it so that we could cut it out and make sure that we were ignoring it. When you walk around, your body also has a change in voltage because you're moving. So that was another thing, is you have to, for very low frequencies, we had to cut those out. So there's a very specific range that we had to start looking at and start filtering out. And that's what the electrical engineer is more focused on for our project, where I use the signal they took in and process it my own way. So when you're dealing with analog signal, this is their bread and butter. These are Fourier transforms. So if you look at this, it looks very jumbled and very difficult to really discern what's going on. So if you have an equation to go with it, and you have a way to look at what's going on in a circuit or what's going on in a signal, you then can start breaking it down into components. And this will basically take your signal and start breaking it down into ways that you can start expressing it in different ways so that you can actually look at it in a more helpful light, or look in a way that you'd prefer to look at it. And I don't remember a lot of these, I'll be honest, because these are not the simplest to deal with, and it comes down to how the components behave in a circuit, and inductors, transistors, or inductors and capacitors and all that. So you have to, when you're dealing with electrical, you're doing a lot more, or I don't want to say a lot more, but you're dealing with a different type of math. You're dealing more with calculus and all that, where digital is more, you could lean more towards linear algebra. So that was more of the electrical aspect of computer engineering. So let's go more into the coding part. So why are there so many languages? You got Rust, C, C++, Python, C#, Swift, all these different things. And this comes down to what they're used for. So if you want to make a website, you do HTML, CSS, JavaScript. Well, you could also do Rust, but it's more of what you need out of it. And these languages are built with inherent flaws. So I would never use JavaScript as a security website or as a security purpose. It's just a bad idea. Where Rust is, you have much more of the security built in with it, and you have a lot more of that considered, but it's a lot harder to work with. There's a much larger learning curve to go with it, where you could go with Python, which is much more easily learned, and it's a little bit better for the everyday person to understand, but it's also slow. So Rust has that advantage where it's faster. C++ has that advantage where it's faster. It's much more low level. And these are compiled down to, there's a million things you could say about different code languages, but they're all just compiled down to machine code and then sent as electrical signals. So you learn all about that in computer engineering, which is a whole different, going into a whole tangent. But basically you have, each one has its own purpose and its own function, its own specialized behavior. And you got to choose which one's best for that. And sometimes you need to learn new language in order to do something else you want to do. Kind of going off of that, you have time and space complexity. So when you're dealing with like basic programming or early programming, you do double for loop and you do all these different things to get it to behave however you want. But when you're dealing with large data sets, when you're going through all of Google's resources, or when you're going through all of a large amount of information, or you're going through a lot of information being fed in at once, you have to think of, how do I optimize this? How do I make it so that the algorithms and data structures take up as little time and space as possible? How do I make it so that I could do something that's really absurd in a very short amount of time? And some things just you can't do. So there's algorithms designed so that it's very slow, and that's more for the security application. But there's also algorithms where it's designed to be fast. So it's just a whole playground of, you have different things floating in your head, and this is really the creative part that comes to coding, is where you have a problem and you have to figure out what's best. So when it comes to space and time complexity, you deal with big O notation, and that's just an easy way of saying, what's the mathematical way of saying that? What's the mathematical way of saying how fast it's going to be at worst case scenario, or how much space it's going to have at worst case scenario? So simple idea is the double for loop, that's going to be n squared, because you're going to go through n amount of times. So just multiply them together. Where hash map, it's a linear, you have a key and a value, and they point to one another, and it takes time to get to there, but it's not like going through the entire array every time you need to access something. So you have all these different tools and pieces that you take out and you apply them, and you just have to, you learn these behaviors over time, and you learn how to optimize it. And it's really a lot about, how can I be the trickiest I could be about this? And this is more of the math that I deal with day to day, is what's the optimization? What am I using here? How can I use it better? This is also the vast majority of interviews. You're going to be dealing with time and space complexity. And once you create a program, how fast is it? How much space does it take up? And sometimes it's going to be n factorial, and that's the best you could do, but that's sometimes the best you could do. So it's just a matter of, this is the bread and butter to the coding part, is you use this day to day, you use this for interviews, you use this for everything. And it's not really talked about until later, usually, in coding. So that kind of gives you a good idea of computer engineering versus computer science, electrical engineering. Now, a little bit more about what I do. So I worked with blockchain for a while there. For a couple years, almost 3 years. This is very common to be considered Bitcoin, Ethereum. So what Ethereum does differently than Bitcoin is it takes the concept of blockchain and basically says, let's program on top of it. So in a very basic sense, blockchain is trying to secure something, trying to secure information using a crowdsourced method of discovery. So you have this information, you verify that it's good, and you verify that this is true, and everyone works off of that truth, because it just takes 51% of people to say that's true in order for it to be the accurate information. And then if you have someone come in and say, well, I'm going to toss in my own information, I'm going to toss in information that's going to be useful for me and like give me money, then everyone in the 51% can say, you're not playing by the rules, this is the rule book, we're just going to ignore you. So the concept is very much trying to secure something using the logic that no one trusts anyone else. And it's susceptible to 51% attacks, where you have 51% of people agree on something that isn't true, or agrees on something that breaks the rules. But in order to get there, you have to have 51% of the network, which is billions of dollars investment to just do simple things. And it works off of this whole concept of trust. And that's why it's kind of a currency. That's why they use it as a currency, because you have this concept of, you trust the US has this amount of, the US dollar has this value, European euro has this value. And that's how currency is determined. But for this, it's more of the network trusting it. So it's its own different dynamic, which is very unique and very, I hate to say it again, but it's very different from what previously has been used. And this is used for basically zero trust in, say, a database or something else. So you kind of expand that out to, so it works for currency in that way. Now, if we have to have 20 parties participating in, or 20 people participating in a database, and that database, such as who owes what bank, if these banks all say the same thing, or one bank out of it says something different than every other bank, they say, we don't trust you, they go with the status quo. And this kind of gets into how banking can be done differently and all that. It takes zero trust as a new concept. And this is useful for different applications, such as advertising, where advertisers and people who display advertisements don't trust each other. Naturally, they want to cheat each other out of money. So you try to put a layer in there where you only put trustworthy parties that have behaved properly, and people can boot them out. And it becomes a whole other layer. And my team specifically at Consensus did this for satellite spotting. So this is tricky because you have different governments saying different things, and they'll poison databases of satellites. And you basically say, everyone participate in the system and go ahead and put in satellite observations, and we could go ahead and track these satellites. And that could be used in order to get governments and all these entities out of the way and just say, this is what's up in the sky and what we're observing. This can be verified by X amount of people. We trust that's there. And this was actually built from built off of the idea of spy satellite observers and what they like to do. And that is put out information on spy satellites. So I'll go ahead and open up, kind of giving you a better idea of what's going on here. So trueset.org, this is what we built, and just kind of going through it. But you have entities, you have satellites, and this is basically the idea that we don't trust anyone, or we don't trust anyone in this. But if there's enough observations, say in this satellite, we could start trusting that it was observed and that's correct, and all the information is valid. So it's a lot of information to take in, but it's applying this concept of zero trust, because you want to trust no one, you want everyone to participate, and if enough people say it's true, then you trust it, kind of. So kind of wrapping it up, just trying to go past that and try to go past majors and the profession and all that is things to keep in mind when you start working and start dealing with just engineering in general or science or anything. Is you got to keep ethics in mind. This is something that is really not talked about enough, where you'll have higher ups or you'll have someone say, we need to cut corners, but you need to make sure that you do it to your due diligence and do your job right. Design how to make it so that people can use it. Just because they don't understand what you're thinking in your head doesn't mean it's not, doesn't make it clear and doesn't make it the best way to do it. So keep design in mind, keep in mind that you work with other people and that you are making something for someone else. You're not making it just for yourself, usually. collaboration is so key because you have to be able to make large projects. You have to be able to make things that people in the history of humanity have not really been able to do. And that's only done through collaboration. You can't, no single person, I hope, no single person in JPL, say, could make the entire Mars rover, send it up, and call it a day. That's such a, there's so many man hours that go into that. And it's something that you need to learn how to dynamically work with people. And that kind of goes into the next bullet, is being dynamic, working with people, working around people, being able to step away from something and think of it in different lights, and having the willingness to say, I'm wrong, or I may not know the most, or being able to say something where it's just humility. It goes a long way, and it helps you a lot in so many applications. And a lot of these things aren't stressed enough when you go into majors. And I'm just kind of trying to bring it back because these are very important. So thank you guys for listening. If you need to reach out or want to reach out, here's my email. I will stop sharing so that I could actually see if there's any comments or anything. But thank you guys. So, ask from Hannah, what is your favorite part of computer engineering, and what made it click that you wanted to pursue it? So, I think my favorite part of computer engineering is probably the fact that you learn all the way from an electrical signal, 0 volts, 5 volts, all the way up until a computer programming language, and being able to trace it all the way back, and being able to make a program in C, C++, put into assembly, put into machine code, start going through a computer architecture and being able to say, this is the voltage at this point, this is the voltage at this point, and it going from a magical world into a reality and into something that is not many people out there can say they know how a computer processor works, or how electricity goes into something on your screen, or something that you're working on, or being able to process information. It's such a unique thing, and it's such a it's exactly what I wanted to major, and that's why I went into electrical engineering, and I'm glad I switched over because that's exactly what I want to learn. But other people would love electrical engineering and would love computer science, and it's a matter of figuring out exactly what you want and what you need to learn in order to make you or to give you the ability to pursue what you want to do, and what will make it so that you aren't working every day, that you're going to work, but you're having fun and you're enjoying what you're doing. So what made it click was that I was in electrical engineering courses, and I was in all these other courses, but having this professor sit down with me and tell me that what I am doing was clicking for me, and was like being able to, because I didn't think I was a great student. I was like, I don't understand pointers right away. I don't understand all this. And sitting down with the professor and being able to talk to them and see that they saw it completely differently, and that I didn't have that full understanding starting out, but I took the time, and I really tried to understand it. And the depth of knowledge that I got because I struggled with it was really what made it click of, this is really cool. I really like this, because it wasn't just right off the bat I got it. It was, I struggled with it, which means I got all that time to learn a lot more than the person who got it to click and just went on to the next subject. And that's sometimes what happens. And it really helps. It really gives you a much better understanding of what's going on. So yeah, if you have any other questions, feel free to reach out. I'd be happy to answer anything else now as well.
So I have a question. How do you like your company that you work with now compared to the other companies, the previous company that you worked? I know there were 2 sectors in that same company. What's your feeling and what's your comparison?
Yeah, that's actually a really good question. So with my previous company, it was Consensus, which was a blockchain-based company. I've worked remote for 3 years now, more than 3 years. And it's given me this, the previous company was remote first. So it gave me that foundation where they kind of understood what they need to do to get to be remote. And I didn't like some of the aspects of it where my previous one was kind of the concept, or Consensus was more of the concept of consensus. The CEO kind of like stood back and said, you guys do what you need to do. I'll be here and I'll try to guide you if we really need it. Which was a very unique way of doing it, but it was, it gives me a better appreciation for understanding where everyone's role comes in and higher ups and dealing with that. Where if I just went to a company, I would have been so annoyed at the higher ups and they were doing this and that, and I didn't like that. But it gave me a lot of foundation I really appreciated, where I got to work with a senior engineer and really learn a lot from her. It it was very much open. Now, it also had a lot of drawbacks where you don't have benefits of 401k, you don't have all these other things. And I appreciated a lot of the aspect of my manager was very humbling, and he said, you take care of you. My second year there, I had a huge health scare, and he basically said, you take the time you need. We'll be here. If you're ready, whenever you're ready to work or whatever, come back and don't worry about us. And he said, we'll keep working through this, and we'll make sure you have a spot. And it was very, very kind of him. But then, but you also get this idea that you have to do what's best for you. So it was this huge thing of being able to find a balance in life. And then I went on to Aspen Mess, where I really appreciate it because I got in, they said, it's 5 o'clock. I'll finish this up. You don't know enough, so I'm not going to give you any more information. You take the day off, the rest of the day off, because you're done. And they really didn't drag me through the dirt when fires were started early on when I started. But it also has that backbone of, you have a larger company, you have 401k, you have all these benefits. And you stress a lot less when you have that versus a startup culture, where you have to deal with, okay, so is today the day we get canned, or do we get to keep on working? And the important part is that I found in both cases people that said, you need to take care of your health. Your health is your wealth. And that they are very much try to make sure that you don't burn out, because even as employer standpoint, burnout's terrible. And you need to make sure people are able to do their work. So you also need to make sure they're mentally able to, and they go out and take care of themselves. So it's very stark differences between the two. But the key there was that I found people that they were very much trying to make sure people were taking care of themselves. And I can't stress enough how important that is, for especially engineering, where especially coding, where you could be worked to death. And I very much appreciate both my career experiences. I've learned a lot because of them. So
thank you for sharing that.
Yeah, of course.
Yeah, we all go through it, and as people like us, Mr. Alonso, Mr. Hikido, can speak to that, and experiences that we deal with in the, when we start and where we are now is based on what in the past that put us here, in on the road. So, and we're at a point that, hey, we're either already retired, like Mr. Alonso says, or very close to retirement, but we lived a life, and we worked our butts out get things done, and we had to prove ourselves, from right from the beginning, and we've done that, and we've been laid off as well. I mean, I've been laid off 3 or 4 times, but I always seem to find something the next following week, something already lined up because I was told ahead that, that the wave was going to come.
Yeah.
So, and I've had very good managers and supervisors and what have you that gave me a heads up and say, don't worry about this right now. Concentrate on what you need to do, and health is, is first. You have to take care of yourself first before you keep on working, and then your family's first. Your health is first, and then your work and what have you. So I'm glad you are doing fine right now, and you experience wasn't a pleasant experience, but you figured things out, and I'm glad you're in the right direction.
Thank you.
Congratulations.
Yeah, you learn a lot. You learn a lot through adverse situation, and I try to tell other people these things. I know it might always stick, but it's important to say, you got to take care of yourself. You've got to, like, your employer's looking out for your employer, and you're looking out for yourself. That's how it has to be. And I mean, even with college, 2 of my grandparents had passed away the first 2 years of college, and it's when that happens, you have to take a step back and see, okay, what do I need, and how can I talk to the professors to try to get what I need, because the professors are also trying to do what's best for you too. There's no purpose for them to make it hard for you, and the vast majority of the professors are going to talk with you and work through any difficulties you have. And you have to be your best advocate, because that's the only way you could get things that you need taken care of.
So true. Any other questions? I see quite a few alumni. There's Carlin, who is also an alumni. I don't know if he's willing to give a talk as well.
Well, maybe not soon, but eventually.
The next time around, huh? Okay. How you doing?
I'm doing all right. Gearing up for the last year of my PhD, so lots to do.
Oh yes, very good. Still in physics or?
Civil engineering, transportation engineering. So physics was a while ago, actually.
I remember I tried to help you. I mean, I did try to help you, but you were pretty young back then. I mean, you're young now, but
yeah, did a lot of changing and thinking. Since
there
then,
you go.
Yeah.
But anyways, good to hear from you. Any other questions? And if not, then thank you so much, Kenan, for spending time with us
Thank you.
and the advice that you've given us or giving to the students here. And your leadership was very welcome when you were at Oxford. I really had the honor to help, work with you and try to help you out as well, and Mr. Wright. So I think we were only 2 mentors, or maybe 3 mentors when you were there.
Yeah, I think there's also Mr. Wright and then Mr. Miller.
Yeah, Mr. Miller. Yeah, Mr. Miller, he's been MIA, so for at least 3 or 4 years. So I try to keep him on board, but he just hasn't responded. But we have maybe more than 15 mentors altogether, and Mr. Tom Hipito is our newest mentor and works for Boeing. I think in Bowling. In what part of the city do you work in? And
So,
which Boeing do you work?
oh, I work for Boeing in El Segundo, so satellite division.
Okay.
So yeah, I think next Saturday, right? I'll kind of give you a intro about me, a little background. I'm a mechanical engineer. So I've been there 29 years. So yeah, we can next week we'll talk a little bit more about.
All
But
right.
I'm not gonna be able to get into details just because of
No.
Boeing policy and some of the
Right.
stuff I work on. But I'll give you my background, and you know, it's great to be able to work with your team. And unfortunately, this year, right, with the COVID, it's a challenge for everyone. But
Yes.
you know, we're learning new ways.
Yes.
Like every challenge in life, right? We have to overcome, right? We can't let them be hurdles and hold us back. We figure out we're smart people. We'll figure out how to overcome and adapt.
Right.
And you know, we'll do the best we can, and we'll get over this. And so yeah, so next week,
Awesome.
we'll talk a little bit more. So yeah,
Oh,
yeah, I do
tuned.
appreciate you inviting me to these because I find them all very informative, and I'm glad a lot of alumni are actively participating back, giving back. And like you were mentioning, how you know, you have people looking out for your well-being, and hopefully that ethics is being embedded in you. And as you grow older and become what, you will, you know, bring that back, and you will now be the ones looking out for fellow, you know, people coming up, and everyone listening in today, right? It's not just about learning new stuff. It's like, okay, how do you pay that back? You remember what
Exactly.
people did for you. That just becomes your way of life. You just become a better person, and not just technically, but in general, right? And I think that's how we become a better society, is we help each other out versus bringing each other down. So yeah, that's good. Good to hear.
Great. Well, thank you. Yeah, you guys are welcome, alumni, to hear in our next. We have two speakers, that, like Mr. Tom Hikito, he'll be speaking on Saturday next week. But on Friday, we do have a special guest speaker from JPL, a robotics engineer, and it's actually a researcher, robotics researcher, engineer slash. So stay tuned. Please join us next week.
Thank you. Thank you guys very much. Let me know if there's anything I can do to help out.
Great. Thank you so much, Kenan.
All right. Have a great one. Thank you, everybody.
Have a good weekend.
Have a nice weekend.